So let me share my screen just a moment. Okay. So thank you again for participating in this seminar. And today's lecture is on um, climate smart city and the urban development. And in this research, me and my colleagues, we try to answer to this question that whether uh, co-integration and whether joint development of um, climate-related policies and a smart development can help to cope with the uh, carbon emission issues, especially in the cities, because the high level of emissions, especially in cities, is one of the major issues, and it is making a significant part of the total emission of the country. So if we can find a solution for uh, making the cities cleaner, making the urban environment cleaner, then this can reduce the total emission of the country drastically. So, in order to answer to this question, we have done an empirical work, and that in this presentation, I'm going to explain it. So, yeah. The result of this study is published uh, in the Climate Change Economics Journal in 2024 with the same title, Climate Smart City. Can China's smart city policy lead to low carbon development of cities? Yeah, so this is what we uh, aim to answer in this research, and this is a joint work with my colleagues Kang In Dong and Kong Yu Zhao. So, yeah, this is the background. As I mentioned earlier, um, high level of emissions in urban areas, in cities, is one of the major challenges towards sustainable development, and metropolitan cities contribute approximately to 60% of the global gross domestic production and consuming about 80% of the world energy. And because of this high contribution to economy and high consumption of energy, significant parts of the global emission is coming from cities. Almost 75% of the planned CO2 emission is coming from cities, coming from urban areas. In China, the level of CO2 emission in the year 2000 was almost 3,000 million tons, that it increased to more than 9,000 million tons in 2017, and it's almost threefold increase. So CO2 emissions have a more profound and long-lasting emissions comparing to other types of emission, and these have more impact on our environment. This is the reason that we mainly focus on CO2 comparing to other types of emissions such as NOx, SO, and particulate material and so on. In this research also, we are focusing more on CO2. The Chinese government has proposed achieving a carbon peak by 2030, and after that, reducing the level of emission and achieving carbon neutrality by 2060. Extensive traditional urbanization has brought about a series of problems. So when we have high level of emission in our cities, there are significant issues that we call them urban disease. such as traffic congestion, resource shortage, health issues, and environmental deterioration. And sustainable development of cities is in line with SDGs, with Sustainable Development Goals, especially Goal 11 of the SDGs stresses the importance of making cities inclusive, safe, resilient, and sustainable. So this is about sustainable cities. On the other hand, the second keyword of our research is a smart city. So what does a smart city means? The term smart city, it means that we used several technologies, new technologies in the buildings, in power grids, in highway, including sensors, in order to make the dynamic of their operation more efficient in the term of energy usage, spatially. So this means a smart city in the field of energy usage. It means utilizing new technologies, sensors in buildings, in power grids, in highway, in order to make their operation more efficient, more energy efficient. The Chinese government has formulated a series of policies to promote the implementation of smart city pilot projects. So here I listed three of the major policies. However, the policies that set by the Chinese government is not just limited to these three, but these are the major ones. In 2012, the notice on carrying out the National Smart Pilot City and the National Smart Pilot City Index system were issued. Next, in 2014, Chinese government issued the National New Urbanization Plan. And then government at all levels, in the central government and also in the local government, have paid special attention to smart city construction. Then in 2015, the guidance on the construction and application of a smart city standard system and evaluation index system was issued. And the objective of this guidance was to accelerate the formulation of relevant standards and officially putting the standardization of smart city on the national agenda. So this means existence of these kinds of policies, guidelines is showing the importance of a smart city, and this is also an evidence for what we aim to assess, that Chinese government also understood the importance of a smart city in order to achieve to a more efficiency in energy consumption, for reducing the level of emissions, and for achieving the carbon neutrality. However, in this research, we are going to assess it empirically. So this figure is showing the spatial distribution of three batches of pilot cities in 2012, 2013, and 2014. A smart city, pilot city that has been entered. And as it is clear, in majority of these cities initially used to be in the eastern and southern part of the country, which are more developed, in Guangdong province, in Zhejiang province, Jiangsu province, and other eastern and southern provinces. And then gradually it has been expanded also to central parts of China. And then in the future, it will be also expanded to other parts of the country. So why the country is more, why the government is more focusing on these regions and the pilot cities were in the eastern and southern and southeastern part of the country? Because these regions are more developed, therefore have a higher level of energy consumption. As a result of that, have a higher level of CO2 emission. And this figure is an evidence for what I have mentioned, that the darker the level of blue color, it means that the higher the level of emissions in different cities. Yeah, this is provided in this figure. And yeah, regarding the research question, in this study, we aim to answer to three major questions. The first question is this: can a smart city policy realize economic growth and environmental improvements simultaneously? It means implementation of a smart city policy can result in green growth of the country. Green growth, it means simultaneously we achieve the economic growth and environmental improvement. So this means green growth or sustainable growth. This question examines whether the implementation of smart city policies can concurrently enhance the economic development and reduce the level of CO2 emission in Chinese cities. The next question is, how does the smart city policy influence CO2 emission? So this question explored the mechanisms through which smart city policies impact CO2 emissions, including the direct and indirect effects such as scale, structure, and technology effects. The third question that we aim to answer in this research is that, do heterogeneous effects exist in different cities? This question investigates whether the effects of smart city policies on CO2 emission vary across different types of cities, such as first tier, second tier, and third tier cities, as well as across different regions, Eastern, Central, and Western China. And regarding the contribution of this study to the literature. So this study is doing, is contributing in three different aspects to the literature. First of all, employing a difference in difference methodology to explore the causal relationship between a smart city policy and CO2 emission. This approach not only evaluates the marginal impact of a smart city policy on emission mitigation consistently and efficiently, but also enrich the landscape of a smart city research. Next, the paper delved into the mechanisms underlying the impact of a smart city policy on CO2 emission from the perspective of scale, structural, and technological effect. This is essential for understanding the advantages of smart cities and provide policymakers with crucial reference points to further propel the development and implementation of smart city projects. The third contribution of this study to the literature is that the study examined the heterogeneity of a smart city policy effect caused by differences in city size, city level, and resource endowment. This helped to better discuss the heterogeneous environmental effects of a smart city policy and ensure that the policy's implementation is effective in various types of cities. So in order to run this research and in order to find the contribution of this study to the literature, we have done an extensive literature review. The first batch of studies that we reviewed are studies on the smart cities and CO2 emission nexus. So some scholars argue that the development of smart cities or urbanization may lead to environmental pollution, such as Grossman and Kroeger 1995 found a close correlation between urbanization and the greenhouse effect. This conclusion is supported by Khairil, 2011, who highlighted the serious impact of urbanization on local ecosystem from the perspective of land use. Conversely, many studies propose that smart cities help reduce environmental pollution and improve environmental quality, such as Hesary 2013 asserts that smart cities can improve urban green total factor productivity by reducing CO2 emissions and using more efficient energy. In another study, Liu and Peng 2013 support this viewpoint, concluding that in smart cities, the utilization of natural resources shifts from a linear structure to a network structure, thereby saving resources and continuously improving efficiency. In another studies, Khansari et al. And Ramaswamy et al. 2016 reinforced this finding by showing that advanced regional energy system can enhance the supervision of energy use and pollutant emission. Numerous scholars have conducted empirical analysis based on China's smart city policy and supported the positive impact of a smart city on environmental quality, such as Damerly et al., Wu et al., Yang and Chong confirmed that a smart city contribute to reducing CO2 emission and enhancing urban environmental quality. Additionally, some research indicate a non-linear relationship between urbanization and environmental pollution, as noted by Earhart, Martinez et al. And Martinez, Zarzoso, and Marotti 2011. However, another study by Igit Kanlar and Kamruzaman 2018 highlight that the impact of information technology development brought about by a smart city policy on urban resources and the environment remain uncertain. When we reviewed the literature, we found out that there are various factors that have been identified as influencing CO2 emission, including economic development, industrial structure, energy consumption, and technological progress. Zhang and Tan discussed the relationship between population factor and CO2 emission, highlighting the significant impact of population aging. Or in another study, Haler Mariam et al. Examined the linkage between carbon emission, income inequality, and economic development, indicating that economic growth can derive CO2 emission but also provide opportunities for mitigation through technology and policy intervention. When we reviewed the literature, we found out that there are three gaps in the literature that we aim to fill it. First of all, lack of consensus on environmental impact. Some research suggests that a smart city policy can mitigate CO2 emission and improve environmental quality. Others point out potential negative effect or highlight uncertainty in the outcome. Secondly, heterogeneity of a smart city policy effect. There is limited exploration of the heterogeneity in the effect of a smart city policy on CO2 emission across different types of city. Differences in urban development, environmental regulation, and resource endowment may lead to varied impact, necessitating more detailed empirical analysis to understand these variations. Third gap that we recognize in the literature is insufficient focus on a specific mechanism. Existing research has given scant attention to the specific mechanism through which smart city policies affect CO2 emission. Understanding this mechanism is crucial for formulating targeted policy to mitigate environmental degradation and achieve the dual carbon targets set by the Chinese government. Next, for Yeah. So next we see that in order to run this work, we have developed an empirical model. It is a we use the city panel data, Chinese cities panel data from 2003 until 2017. The dependent variable is CO2 emission that we obtain it from the data set provided by Chen et al. The data on a smart city policy pilot regions and cities were collected from policy document issued in 2012, 13, 14. So as it is clear here, the dependent variable is CO2 emission. Independent variable is smart city policy implementation. Control variables are population, registered population per year in each city, economic development, gross regional product per capita, industrial development, output value of the secondary industry, tertiary industrial development, output value of the tertiary industry, trade openness, degree of trade openness, economic openness, degree of the economic openness, political openness, degree of political openness, human capital, level of education and skill in the workforce, financial expenditure, local government fiscal expenditure, internet economy, development level of the internet economy. Next, for the estimation, in order to analyze the smart city CO2 emission nexus, we introduced CO2 as a dependent variable and policy as the smart city policy as the key independent variable. In addition, we also take population, economic development, secondary industrial development, tertiary industrial development, trade openness, economic openness, political openness, human capital, financial expenditure, and internet economy as control variables. Furthermore, the differences model is selected to investigate the mitigation effect of the smart city policy on CO2 emission. Specifically, the policy pilot cities are selected as a treatment group and non-policy pilot cities as the control group. So in the equation 1, I represent cities, T represent years. CO2 IT is the dependent variable, and treat I multiplied by post T is the core independent variable. Treat I equals 1 if the city is implemented as a smart city, and it is equal to 0 if the city is not implemented as a small city. Post T equals to 1 for all years after policy implementation by the specific smart city, and 0 for all the years before the policy implementation of the specific smart city. Treat I multiplied by post T is the interaction term between treat I and post T. Regarding the estimation model, to eliminate possible heterogeneity in the empirical study, we use the logarithm. So logarithm of the variables are adopted to improve the accuracy of the estimation. And the estimation model can be written as in equation 2, where the differences between a smart city pilot and other cities are shown in treat I by post T. Therefore, beta 1 can be expressed in the more intuitive way. So B1 is equal to equation 3. Equation 3, we have written B1 as in equation 3. We obtained it from equation 2. And in equation 2, beta 0 represent the intercept term, epsilon it is the error term, and the parameter beta j, that j is from 1 to 11, are the estimated coefficients for the control variables in the vector x. And in order to improve the accuracy of the estimation, we take the time fixed effect and individual fixed effect into the construction, and the error terms are also shown. So next, we can see the table of descriptive statistic of the variable that we have, the dependent variable, CO2 emission, and different types of control variables or independent variable that we have here. For the core independent variable, which is the pilot city smart city policy, we obtained it from policy documents in 2012, 2013, 2014. And for all other variables, we can see their statistics here. Population, gross regional product, ratio of secondary industrial output, ratio of tertiary output, and so on. So next, we started to do our empirical works, and in table 2, the baseline regression is provided. We ran the regression using 3 different models in table 2. Results estimated by the pool ordinary least square model are presented in column 1, which does not consider time fixed effect nor individual fixed effect. Results estimated by the individual fixed effect model are shown in column 2, which include city level fixed effect. Results estimated by the individual time dual fixed effect model are provided in column 3, which include both city fixed effect and year fixed effect. Table 2 is the baseline regression results. As it is clear here, in all 3 models, we see that the coefficient of the smart city variables are negative and statistically significant. So next, in this slide is the interpretation of the results. As I've mentioned earlier, the core independent variable, which is the smart city policy, denoted as treat I post T. And in all the 3 model has a statistically significant negative impact on CO2 emission. The result in column 1 indicate the estimate for a treat I post T is 0.0694, 0.0694, implying that cities under the smart city policy are facing harsher environmental requirement than other cities in the control group. Therefore, their CO2 emissions decrease significantly. This is because of, rules and regulations. Secondly, implementation of the technologies also has impact, and because it results in a more efficient use of energy. The results shown in column 2, which is individual fixed effect under strengthen our finding above, and it's clear that the result is significant. Column 3 include both the time and individual fixed effect. The results in column 3 in table 2, it means here, this variable, shows that CO2 emission decreased by about 1.83 after the city became a smart city pilot. In other words, this result suggests that keeping other things constant compared with CO2 emission in normal cities, without a smart city policy, CO2 emission in a smart city declined by 1.83%. The results show that in all cases, the smart city policy is effective in reducing CO2 emission in treated cities, which means that this policy can significantly curb CO2 emission and has certain effect on achieving the dual carbon goal. It means development of the economy and at the same time reducing the level of emission. In terms of control variable, on the other hand, population, economic development, secondary and tertiary industrial development, and finance expenditure can significantly increase the level of CO2 emission. So next we started to do a series of robustness checks in order to make sure that the results are robust. Figure 3 shows that the differences in all variables between the two groups are significantly reduced, which means that the PSM-DID method is suitable for this paper. For the robustness that provided in table 3, after the PSM-DID test, the smart city policy still has a significant inhibiting effect on CO2 emission. More importantly, this effect has improved compared with the baseline results. In some, the above PSM-DID test further verify the baseline regression, as it is clear here the coefficient of DUDT, which is the smart city policy variable, is statistically significant and it is negative. That means that development of smart cities can result in reducing the level of CO2 emission. We have done a further discussion in order to check the heterogeneous effect by regions, and the results are provided in table 4. In order to study the heterogeneous impacts of the smart city policy on cities in different locations, we divide cities into eastern cities, central cities, western cities according to their geographical location, and then we conduct a specific regression in different subsamples. All the coefficients of the interaction term in 3 regions are negative, indicating that the smart city policy has CO2 emission reduction. There's a typo here. In cities in all regions in China, compared to the non-pilot cities in control group, pilot cities under the smart city policy in the eastern, central, and western region can reduce CO2 emission by 3.43%, 0.28%, and 2.5%. That these percentages are coming from here. The smart city policy has the largest policy effect in the eastern cities by showing the most remarkable mitigation effect on CO2 emission, while the policy effect in the central and western regions are less remarkable. In order to study the heterogeneous impacts of a smart city policy on cities of different levels, we divided all cities into 3 groups: first-tier cities, second-tier cities, and third-tier cities. And then we conducted a regression in different subsamples. All the coefficients of the interaction term in these 3 tiers are negative, indicating that the smart city policy has a significant CO2 emission reduction effect in cities in all levels of development in China. Compared with the non-pilot cities in the control group, the pilot cities under the smart city policy in the first tier, second tier, and third tier can reduce CO2 emission by 15.19, 5.83, and 1.7%. It means the first tier has the highest emission reduction impact. So therefore, we can see that the first tier cities have the largest policy effect, followed by the second tier, third tier, which has the least policy effect. Next, we have done another heterogeneous effect assessment. And we divided the whole sample into large cities, small cities, and then conduct regression in different subsamples to explore the different specific impact of the smart city policy on CO2 emission between large cities and small cities. All coefficients of the interaction term in these cities are significant and negative, indicating that the smart city policy has CO2 emission reduction impact regardless of the size of the city, whether the city is big and medium size or the city is small. However, this policy has more impact on big and medium sized cities compared to small cities. And the smart city has a more pronounced effect on CO2 emission in big cities, as I have mentioned. Next, we have done another type of categorization, and we assess the heterogeneous effect by city resource endowment. We divide all samples into resource-based cities and non-resource-based cities. All coefficients of the interaction terms are significant and negative, indicating that the smart city policy has significant CO2 emission reduction effect in cities in both the resource-based group and non-resource-based group. Their smart city policy significantly reduced 3.61% of CO2 emission in non-resource-based and which is almost 1% higher than the impact on the counterpart. In other words, the smart city policy has a more obvious CO2 emission reduction effect on non-resource based cities. So why this is existing? Because in more resource based cities, consumption of fossil fuels is more relevant because of the availability of the resources. This is the issue. Next, we have done another step for assessing the mediation effect and for analyzing the mediation effect. Given the significant effect of the smart city policy on CO2 emission, we have done a further investigation. We decomposed the total effect of the smart city policy on CO2 emission into a scale effect, a structural effect, technology effect. Specifically, the level of economic development, the ratio of tertiary industry output value, and the government expenditure on science and technology are taken as proxy variable of scale effect, structural effect, and technology effect. So where the scale, structure, and technology are mediating by three variables that we provided here. Delta 1, Delta 2, Delta 3 are coefficients of the smart city policy, and Theta 1, Theta 2, Theta 3 are impact of these mediating variable on CO2 emission. If all these variables are significant, then the mediating effect can be recognized. Next, in table 8, we have assessed we check the presence and the type of mechanism impact between a smart city and CO2 emission that provided in table 8. The coefficients of treat I post T in model 1, 3, and 5 are statistically significantly positive, indicating that the smart city positive play a significant role in increasing cities' output, promoting industrial structure transition, and encouraging technology innovation. More specifically, the smart city policy can lead to a 3.63% increase in economic development because the coefficient in this equation is economic development. And next regression is showing that 9.81% increase in industrial structure upgrading and 38.83% increase in technological progress. So the smart city policy has the most remarkable effect on the driving technological progress, and after that on the structural effect, which is the industrial structure upgrading, and next on the economic development. The coefficient of scale, structure, and technology in model 2 4, and 6 are significant and positive, negative, and negative, which shows that the scale effect effectively promotes CO2 emission, while the structural and technology effect can effectively reduce CO2 emission. The scale effect contributes to a 10.29% increase in CO2 emission. The structural effect contributes to a 12.45% decrease in CO2 emission, and the technology effect contribute to 1.64% decrease in CO2 emission. Next, so figure 4 shows the mechanisms of the smart city policy affecting CO2 emission. We have the direct effect. We also have the indirect effect. The results of our analysis shows that the smart city policy has an indirect effect on CO2 emission through three mediating variables: scale, structure, technology. While the scale effect tend to increase CO2 emission, the structure and technology effect contribute to reducing them. The interaction between these effects lead to a partial offset, while the positive impact of the scale being countered by the negative impact of the structure and technology effect. Overall, the baseline regression shows a negative net negative effect of a smart city on CO2 emission, demonstrating that the combined reduction from the structure and technology effect outweighed the increase from the scale effect. Therefore, the smart city policy successfully achieved CO2 emission reduction through these indirect mechanisms. Let me conclude my presentation, and then after that provide some policy recommendation. This study empirically investigate the relationship between a smart city policy and CO2 emission using the city panel data from 2003 to 2017. The main finding of this paper are as follows. First of all, the implementation of a smart city policy significantly inhibits CO2 emission. The policy reduced CO2 emission by approximately 1.83%, and as evidenced by baseline regression result and validated through the propensity score matching difference in difference method. Second, the mechanism through which a smart city policy impacts CO2 emission include scale, structure, and technology. The scale effect tends to increase CO2 emission due to economic growth, while the structure and technology effect reduce emission by promoting cleaner industry and improving energy efficiency. Third, the effect of a smart city policy vary across different type of city. First tier cities in the eastern region, resource-rich cities show more pronounced reduction in CO2 emission compared to other cities. This indicates that the effectiveness of a smart city policy is influenced by a city's economic development, geographical location, and resource endowment. Furthermore, a specific component of a smart city policy, such as transportation infrastructure, can have varying impact. While transportation infrastructure may exacerbate CO2 emission, advancement in transportation technology exhibits significant potential in reducing the emission. And regarding the policy implication, we provide these below policy implication out of our study. Enhancing smart city development. The study highlights the importance of promoting the construction of expansion of a smart city. Governments should continue to support a smart city initiative to achieve the dual carbon target of peaking carbon emission by 2030 and achieving carbon neutrality by 2060. Enhancing a smart city policy can improve local governance efficiency regarding environmental issues by integrating advanced technology like the Internet of Things and big data to monitor and manage urban systems more efficiently. And two other policy implications are tailored policies for different cities. As we have found, the impact of a smart city policy on the level of emission is different for the size of city, level of economic development, and resource endowment. This means that in order to achieve the carbon neutrality, we need to have a tailored policy for each city or for each group of cities specifically. Next, we showed that the role of technology is very important and has a significant impact in mediating and in amplifying the impact of a smart city development on achieving a low carbon situation. Therefore, increasing investment in new generation information and communication technology, ICT, such as cloud computing, and fostering an innovation-friendly environment are crucial. These include establishing innovation platform for small and medium-sized enterprises and research institutions to promote the digitalization and industrial upgrading of a smart city. Transportation technology, among other sub-indicators of a smart city, has the most significant potential to reduce CO2 emissions. Innovation in transportation, such as integration of AI, video cloud, and Internet of Things in urban system, can significantly enhance operational efficiency and reduce the emission. Thank you very much for your attention. Yeah, this was